Hey, welcome back to Abstract Algebra. In this video lecture, we're going to wrap up our work in section 4.5 about polynomial rings over a field. And in particular, I want to develop the notion of what an irreducible polynomial over a field is. So you can see our outline here. I'll just kind of walk you through it. I want to define what I mean by an irreducible polynomial over a field. And then I want to prove kind of what will be our main result. We're going to use it next week in this final construction I want to show you in polynomial rings. I want to show you that a polynomial is irreducible if and only if the ideal it generates is maximal. So my handwriting is a little bad here, but that's theorem 4.511 in this section, and that's really the kind of main result. And then this section has some more results in it. We're not going to kind of get into them and prove them, but I do at least want to discuss one of them. It's theorem 4.512, and it's kind of the polynomial analog of what people usually call the fundamental theorem of arithmetic in number theory. So I'll state the fundamental theorem of arithmetic later on if it's not familiar to you. But basically, I mean, what you should keep in mind throughout this whole lecture is that irreducible polynomials kind of play the role of primes. We've already seen in our work so far in section 4.5 that the ring of polynomials over a field behaves a lot like the ring of integers, right? They're both commutative rings, they both have unity, they're both integral domains, they both have the property that every ideal in them is principal, they both have a division algorithm, so they're very similar rings, and this notion of irreducibility in the polynomial ring is kind of the direct analog of prime numbers in the integers. All right, so that kind of makes sense. We've already seen in the ring of integers that an ideal is maximal if and only if it's generated by a prime. And so this is just kind of, more and more consistent with this analogy between the polynomial ring and the ring of integers. All right, so in particular, there's this fundamental theorem of arithmetic. Theorem 4.512 is not out of our reach. We have all the tools that we need. You can certainly read this theorem and digest it. The proofs of it are actually no more difficult to digest than anything that we've done so far in our ring theory and our polynomial rings. I'm just going to leave it to kind of a conversational level here, trying to keep this video short, and really I don't absolutely need the result of theorem 4.512 to accomplish what I want to do with you guys next week, which is talk about sort of the origins of polynomials in your algebraic history back in middle school and high school, finding zeros for them, finding numbers that you can plug into quote unquote polynomials and make them zero. That's what I want to show you next week. Okay, so let's get going. Trying to keep this short. As usual, I'm going to talk a mile a minute, so you can pause this thing as we're going, write stuff down, think about it, read in your book, use the internet to read some other sources, trying to digest this material. Always throughout this stuff, when I'm talking about rings, you can definitely keep in mind things like the integers. When I'm talking about fields, keep in mind things like the rational numbers, the real numbers. You have guiding examples to think about this stuff. When I'm talking about polynomials over a field, think about polynomials over the real numbers. So you can always kind of stop and kind of explore stuff in a concrete setting where you already have a lot of experience. Okay, so let's look at this definition. You're already looking at it there. I have a field f and I take some polynomial in it. I'm calling it f of x. So I'm going to call that polynomial irreducible over f. So there's blue term to make a flashcard. Polynomial is irreducible over f. It's kind of a two-element checklist. The first thing is that it has to have degree at least 1. All right, this is kind of just a technical thing, but constant polynomials are never irreducible. The zero polynomial is not irreducible. Non-zero polynomials aren't irreducible. If I'm talking about irreducible polynomials, I mean that they have at least degree 1. Okay, and then the second part is that whenever you factor it, whenever you write f as a product of g and h, and I certainly here mean that both g and h are polynomials over the same coefficient field. So whenever you factor f into g times h, you factored it kind of trivially. Either g or h is a constant. Yeah. It can't be 0 because if g or h were 0, then f would be, and we've already said f has degree at least 1. But so that's the idea. This is kind of the analog of prime. If you want me, I'll underline while I say these things. A prime integer, well, it's not 1. 1 is not a prime. but it has the property that whenever you factor it into two integers, one of those two integers is equal to 1. Yeah, so that's kind of the exact analog of this. An irreducible polynomial has degree 1 at least, or higher. And whenever you factor it, you factored it kind of trivially. You factored it into just some constant times some other polynomial or vice versa. Okay, so irreducible polynomials are polynomials that kind of cannot be factored in a non-trivial way. Good. So all I've written down here is kind of the language I was already using, but this is important. I definitely put this. I hope you're making kind of a list of results about everything that we're proving here. And this should definitely go in the list, that the units in the polynomial ring are precisely the non-zero constant polynomials. Yeah. If you're an invertible element in the polynomial ring, it means that you're a non-zero constant polynomial, and that's it. All right. So another way to say what irreducible means, a polynomial is irreducible. Well, if it's not a unit, but whenever you factor it into a product of two things in the polynomial ring, one of those two things has to be a unit. All right. That's actually kind of a launching point. You can define irreducibility in other rings that way. You can say an element is irreducible if it's not a unit, but whenever you factor it in the ring, one of the two factors is a unit. It's just sort of an easier way to say the definition. We won't develop in this lecture a lot of tools for showing a polynomial is irreducible. In general, the problem of showing a given polynomial over a given field is irreducible over that field. It can be quite difficult, actually. Not for polynomials of small degree. That'll be sort of our best result. We're going to have some sort of limited results about this next week, and I'll show you that if the polynomial has degree 1 or 2 or 3, well, degree 1 polynomials will turn out to always be irreducible. But if it has degree 2 or 3, I can give you a way of kind of determining quickly whether it's irreducible. But for arbitrary polynomials, it can be quite difficult in general to determine whether a polynomial is irreducible. But I want to do an example. I'm going to borrow a fact without proof here, but I do want to emphasize that when I'm talking about a polynomial being irreducible, I've already kind of committed the sin in this lecture. I need to always say irreducible over what, because it depends. If you change the coefficient field, you could take a polynomial that was irreducible over one field, and it might not be irreducible over another if that other field contains your first one. So let's look at this specific example. So I claim without proof here, I'll prove it to you next week, that the polynomial x squared minus 2, it has rational coefficients. Its coefficients are 1 and minus 2, and those are both rational numbers. I claim that polynomial is irreducible over q. All right, I'm not going to prove that to you right now, but I claim it's true. It's an irreducible polynomial over q, but it's not irreducible over r, because over r, the polynomial f factors into those two linear factors, neither one of which are a unit. All right, so when you talk about a polynomial being irreducible, you really have to say irreducible over what? Because sometimes it won't factor over one field, but it will factor over another. Yeah, you've seen examples like this back in high school algebra, maybe not with q and r, but you certainly can write down polynomials that won't factor over the real numbers, but they will factor over the complex numbers, right? In some sense, every polynomial factors over the complex numbers. Yeah, if this course had sort of not been jostled into pandemic mode in the middle of March, that's something that we may have actually ended up kind of being able to prove in this class. But I think next week the best I'll be able to do is give you some ideas of how you might go read and learn about such a fact. Okay, but I digress. So we've got a notion of irreducibility. You guys understand that polynomials over a field are irreducible over that field if they won't factor in kind of a non-trivial way. So let's get down to the business of proving this main theorem. Theorem 4.511. So here's the statement of it. You have a field f and you take a polynomial p of x in it, okay? And then the statement is that the ideal generated by p, so I'm writing it in that ideal notation, the principal ideal generated by p is maximal if and only if p is irreducible over your field. All right, so the irreducible polynomials over f are precisely the polynomials that will generate maximal ideals, is what the theorem says. Okay, Pause this video a lot. I'm going to be using a lot of technical terms, but this is a good chance for you to remember principal ideals, maximal ideals, our brand new definition of irreducibility. So I'm going to talk fast, but you can stop me. Stop me and digest this stuff at your own pace. Okay, so let's start by supposing that this p of x, I'll just use the theorem to quantify my variables so I don't have to rewrite it all here. Let's suppose that p of x generates a maximal ideal. All right, so let's say a couple of technical details here. So first of all, then that ideal can't be 0, because 0 is not a maximal ideal in the ring of polynomials. 0 is contained properly in lots of proper ideals. So p of x can't be 0. It's not the 0 ideal. Okay. Also, because it's a maximal ideal, it's not the whole ring. Maximal ideals, by definition, are not the entire ring. So I can say from those two inequalities, those two non-equalities, these two things, that p can't be a constant polynomial. It can't be the 0 polynomial because it's not generating the 0 ideal. And it can't be a non-zero polynomial because if it were, it would be a unit. And if it were a unit, the ideal it generates would be the entire ring. All right, so that's our first, because I'm trying to show p is irreducible. Hold on, I'm going to scroll on you here. P is irreducible. There's two item checklist. We just got item 1. That this polynomial p cannot be a constant polynomial. Its degree has to be at least 1, okay? Now I'm gonna go for item 2. Item 2 says that if p factors, one of the two factors has to be a unit. So my proof starts off by saying, well, suppose p factors over the field f, all right? So I've got two polynomials with coefficients in f. Their product is p, okay? I wanna try to show you that one of those two polynomials has to be a unit. I don't know which one, but one of them needs to be a unit. So here's how we're going to do it. Well, if p is equal to f times g, then p is an element of the ideal generated by g by definition. Yeah, the ideal generated by g, this is really an important definition. It is by definition the set of all polynomial multiples of g. So if p is a polynomial multiple of g, it belongs to this ideal by definition. And because the ideal generated by g is an ideal, if p belongs to it, then any multiple of p will belong to it, okay? So the entire ideal generated by p belongs to this ideal generated by g. I could have picked f here too. I'm just picking on one of the two, all right? So good. So if p is this product, then the ideal it generates is contained in the ideal generated by one of the factors. I picked g. But now we're assuming that p of x generates a maximal ideal. So by maximality, this ideal generated by g, it's either equal to p or it's equal to the whole ring, because a maximal ideal is only properly contained in the whole ring. All right, so let's just look at those two cases one at a time. I'm going to start with the second one. If g generates the entire ring, yeah, which is the ideal generated by 1, well, then g must be a unit, right? Because 1 belongs to the polynomial multiples of g. That means g times something is 1. That means g is a unit. All right, that was one of my hoping things. I was hoping that that could be true. So in that case, we're done. If g is equal to the ideal generated by p, well, then g certainly belongs to the ideal generated by p. So g is a polynomial multiple of p, called the multiple h. And now I just need to do a little substitution here. I've got this equation, p is equal to fg. I'm rewriting it. But I just learned that g is equal to p times h. So let's plug that in. Let's take this g and replace it with p times h. And then look at the equation from left to right. It says that p is f times p times h. Well, the polynomial ring is an integral domain. It's an integral domain. P is not 0. It's on both sides of this equation. You can cancel them. You have the cancellation laws in an integral domain. So by using the cancellation laws, that equation implies that 1 is equal to f times h, which means that f is a unit. Okay, so one way or another, the supposition that P factored into this F times H, we were able to deduce that either G is a unit or F is a unit, and that precisely means that P is irreducible over F. All right, take a pause, soak it in. I'm gonna just keep going. We gotta finish the back half of this proof. So now what have I gotta do? I've gotta show you that if P is irreducible over F, it generates a maximal ideal. So let's get down to doing that. So suppose P is irreducible over F, all right? And some technicalities here. An irreducible polynomial, we said, has degree at least 1. So the ideal generated by P is not everything. That's one of the conditions of being a maximal ideal. If you need to stop this, go back to another video, go back to your notes, look up the definition of maximal ideal before we even proceed. Because if you don't have that definition kind of clear in your mind, this proof is going to be a little bit lost on you. So stop it, go back, remind yourself what a maximal ideal is. A maximal ideal is a proper ideal that's not properly contained in any other proper ideal. So I've just shown the first part. This ideal generated by P is proper. So now if you've got the definition of maximal ideal down, it makes sense why I'm making this next supposition. I'm saying, suppose I have some ideal that contains P. Why do I know it's so special? This ideal is the ideal generated by some G. I know that because f of x is a principal ideal domain. Every ideal in f of x has the form parentheses polynomial for some polynomial. So I'm just naming it G. Okay, so my goal is to show you that one of these two set inclusions is actually an equality. If I can show you that one of those two set inclusions is an equality, then I will have met the definition of maximal ideal. Cool. Okay, so suppose that we have this chain of ideals. Well, since P belongs to the ideal generated by it, it must belong to the ideal generated by G. So P must be some polynomial multiple of G, called the multiplier F. All right? But P is an irreducible polynomial. P is irreducible over our field F. So one of these two factors, little f or little g, has to be a unit. By irreducibility, one of them is a unit. All right? So we'll just look at the cases one at a time. If it's G, if G is a unit, well, then the ideal it generates is the entire ring. So we end up getting this set inclusion ended up being an equality. Good, I'm happy. I don't care which one it is. I just want one of them. If it's not G, then it has to be F. So if F is a unit, and let's note, by the way, here that F can't be 0. F can't be 0 because if it were, P would be, but P is an irreducible polynomial. Its degree is at least 1. So F has to really be a unit. It's not 0. And then we can just take this equation, P equals FG, and write it, well, just multiply both sides by the inverse of F. I know I'm writing F of X, but remember, F is a unit. It's a constant polynomial. So it has an inverse. And G is equal to that inverse times P, which is certainly a polynomial multiple of P, right? So if G is in the ideal generated by P, well, then its whole ideal is in there, but the ideal generated by P was already a subset of that, of the ideal generated by G, so they're equal, all right? So in the case that F is a unit, we end up getting this equality. Okay, good. So in either case, one of those two things had to be an inequality, and that's by definition why P is a maximal ideal. Nice. Cool. So why do I care about this theorem? Next week, this will be a very important theorem for us. I'm just going to kind of tease you a little bit with it right now, but let's remember that, we just proved that if P is irreducible over F, the ideal it generates is maximal. Maybe you remember from a couple of days ago that if you have a maximal ideal, the quotient by it is a field, okay? So this polynomial ring quotiented by the ideal generated by this irreducible polynomial is a field. Next week, I'm going to show you that that field in a very natural way contains up to isomorphism, but we're just going to say contains a copy of our field F. Yeah, and then I want to show you some more stuff about that new field that is sort of extending F in some sense has some very interesting and cool properties. And this ... is just kind of a teaser. This is what we're going to do next week, our 15th and final week of this algebra course. I want to kind of explore this idea with you. Okay, so this theorem that we just proved will be sort of the principal result. All right, so that's the heavy lifting of this lecture. Now, without any more proofs, I just want to kind of point out some more analogies to you guys. Let me start by reminding you what the fundamental theorem of arithmetic says. I've stated this here a little bit, I don't know what the right word is, in a non-standard way. If you grab a number theory book off your shelf and flip to the index and look up the fundamental theorem of arithmetic, they're probably not going to state this thing for anything but positive integers and blah, blah, blah. But I'm trying to make sort of an analogy. And what the statement I'm making here is certainly not untrue. So here's our version of the fundamental theorem of arithmetic for the purposes of this lecture. It says if you take an integer that's bigger than 1 in absolute value, that's just a lazy way of saying that it's not 0, it's not 1, and it's not -1. And as I'm speaking here, I'm going to kind of speak by analogies. So I have an integer that's not 0 and it's not a unit. Yeah, because 0 plus 0 is just out of the question, and plus and -1 are the only units in the ring of integers. So take an integer that's not 0 and it's not a unit. You can always write it as a unit plus and -1 times this product, p1 to the m1 and so on, where the pi's are prime integers and they're distinct, and the m's are positive integers. Yeah. It's called the prime factorization of the integer n. And moreover, the primes that are present, these distinct primes, they're unique. They're completely determined by n. So you learned this fact in grade school, that you can always write an integer as a product of prime integers. And if you use exponential notation, then you can write that product as powers of distinct primes, and the primes are unique. If you only dealt with positive integers, you didn't have this plus or -1 out there. It was always a +1. But I'm just going to kind of restate this, that any non-zero non-unit in the ring of integers can be written as a product of a unit and a product of distinct primes to powers. And the primes are unique. And what are prime integers? Prime integers are things that if you factor them, primes are not 1, and if you factor them, one of the two factors has to be 1. Yeah, so primes are kind of irreducible integers. All right, so if you kind of digested that, let me just scroll up and show you what our author's theorem 4512 is. 4512 says that if you take a polynomial that's degree is at least 1, that is, it's not 0 and it's not a unit, okay, very strong analogy, then you can write it as a product in the polynomial ring where this a is a unit, it's some non-zero constant polynomial, and the p's are distinct irreducible polynomials. The m's, again, are positive integers. So this theorem 4.512, it's really kind of a fundamental theorem of arithmetic for the polynomial ring. It says that every polynomial that's not 0 and not a unit can be written as a product of distinct irreducible polynomials raised to powers. Those irreducible polynomials are uniquely determined by f, and the product is kind of unique up to multiplication by a unit. Okay, so the unit is not unique. You can change that. You could do things like if this is, say, the number 2, then I could put like a 3 times 1/3 times 2 or something like that and call that the same unit. All right. So yeah, we won't try to write the proof of this, but I hope maybe you'll kind of try to read it. It's not all that difficult. We would establish the existence by induction on the degree of n. And then to get the uniqueness, we would need this sort of Euclid's lemma that we already proved in the previous lecture, that if an irreducible polynomial divides a product, it has to divide one of the factors. So if you've had the number theory course and you've seen the proof of the fundamental theorem of arithmetic, you could get that proof out and just change everywhere you have a prime, change it to irreducible, and it just kind of goes through. But I'm going to leave it as this conversation. You can ask me about it in class, but we won't delve into the details of this. Ordinarily, we would in a class like Math 343, but this time I'm making some executive decisions just to keep us moving towards what I think is a more interesting goal next week of showing you how to make these extension fields. All right. So thanks for listening.